back, give us a talk.
Yeah, so I might be a bit rusty. Is this on? Can everyone hear?
It's only for recording you.
Oh, is it? Oh, can everybody hear though? Yeah, you all right back there? So I didn't provide a title, sorry about that, but I'm going to talk about sensitivity analysis and constraint. It's of a global aerosol model and something called radiative forcing. So it's a climate science application, and all models are kind of similar in a climate science world. So I'll be talking about the problems that we face in that world. So global aerosol, it's nothing to do with CFCs and sprays. It's particles, solid particles or liquid droplets suspended in the air. So this is dust, that is an aerosol, okay? When dust gets into the air, it affects the amount of sun's radiation that can reach the surface or is reflected back. So this dust is lighter than that surface underneath, therefore more of the sun's radiation will get reflected back, okay? This here is, these things here are actually trails that have been formed in the clouds from ships that have been going across the sea. So the ships go across and they obviously are chucking out black carbon from their chimneys, or whatever you call them in ships. And they leave these trails. So as you can see, aerosols are affecting clouds in the atmosphere. And if you affect the clouds in the atmosphere, you also affect the amount of sun's radiation. So what this does is it affects the temperature of the Earth, effectively. This we call the indirect effect, and this is my focus, okay? This is called the direct effect, so it's actually the aerosol that are affecting the radiation. This is aerosol affect clouds, affect the radiation. So that's the indirect effect. So I want to know about this. Okay, so as I said, models in climate science world are all pretty similar. The Earth is broken up into these grids, so you get horizontal horizontal grid which measures the latitude and longitude, and a vertical grid which goes up through the atmosphere. Okay, all the work I'll be talking about is all the Earth in terms of the horizontal grid, so I'll be looking at all latitudes and longitudes, but I'm only looking at one model level, and it's where most clouds are formed. Okay, so it's the most relevant model level. And this here is kind of a schematic of what happens to aerosol in the air and how it affects clouds, how aerosol is actually emitted, how it becomes aerosol. Some of it is from power stations, you get little particles in the air, but some of it is gas that comes together to form aerosols. So how the models are trying to simulate how this all happens, okay? Now if aerosol changes, if there's very fine aerosol, clouds become whiter, they get brighter, more of the sun's radiation is reflected back. If aerosol changes, it gets larger, they get heavier, they rain out, you actually get less cloud, okay? But the overall effect of aerosol is opposite to carbon dioxide, it cools the Earth, okay? So it's really important, if we're gonna understand how carbon dioxide is helping to warm the Earth, how is aerosol actually, how has it been counteracting that effect? That's the only way we can predict what's going to happen in the future, is to know both of those things. Okay, so I've kind of talked about this now, but aerosol indirect radiative forcing is actually measured from 2 time periods. Okay, so we look at it, what aerosol did we have before we started industry? How has that changed since we started industry? And therefore, what effect has the aerosol had on the Earth's temperature in this industrial period? Okay, and it depends sort of where on this scale you are. So white to black in the background here is the amount of aerosol in the air. Okay, if you're in this shaded area, there's more aerosol already there. If you add more, it's already saturated. It's not going to have much of an effect. Okay. If you're down here where there was no aerosol, you put loads in it, you're going to get lots more clouds. That is going to have much more effect. Okay, so if you start emitting, if we've emitted anthropogenically, we started off down here, we've created lots more aerosol, therefore we've had a huge effect on this cloud. And like I said, it's actually cooled the Earth. Okay. And this is what we're trying to measure, okay? Trying to look at in terms of what aerosol processes has that been sensitive to? How have we actually affected the climate with our aerosols, okay? So I mentioned this already. Sun's radiation hits the cloud, lots of it will bounce back, and only a bit of it will get through the cloud and heat the surface. If you're in this part where it's dark, lots of it will hit the surface, very little of it will bounce back. So if we started off with this and we changed to this, that's a huge effect on the temperature. Okay. Now what we model are the aerosols that are leading to this, okay? So our global aerosol tells us how many cloud condensation nuclei we have in the atmosphere. So how many particles can the clouds interact with? It doesn't actually tell us about the cloud, it just tells us about the aerosol that's present. We run that through another model, and that gives us what we expect the radiative effect to be of that aerosol. So we have this, we model in this is our state, what is the aerosol in the atmosphere like, but we want to learn about this, which is the change in temperature that has actually led to. Okay, so it's important that I introduce these just so that you can understand what we're trying to actually model here. Now this is all subject to uncertainty because we're using computer models. We can't track every single particle in the atmosphere, so we have to make assumptions about what's going on. And in particular, these particles are a lot smaller than those grid boxes, so we have to kind of approximate what's happening in a whole grid box. Okay, so each of these things that's going on, these processes, is actually happening at a very fine point scale, but we can only model the whole of the grid box. So there's definitely uncertainties there, okay? Now, if we look at this, what we call this from the Intergovernmental Panel of Climate Change, that tries to measure all the things that we're doing to the atmosphere to affect the temperature. Okay, so aerosol is one of these, which is this bar here. So as I said, it's actually cooling the atmosphere, and it's doing the opposite to CO2, which is at the top. The CO2 effect is very well understood, it's well modelled, they're pretty sure what's going on. So it's got a very small uncertainty bar, okay? These uncertainty bars come from different global models, okay? Lots of climate centres around the world have their own model. They're not independent because people move between centres, but they consider them independent because they're doing slightly different things. They just take runs from those different models, compare the standard deviation of the outputs, and come up with these error bars. They're kind of model diversity bars more than anything else. So all the models in terms of what's happening to CO2 in the air agree. They're pretty sure. Now, they're pretty sure that it's a very definite warming. Okay, that error bar doesn't come anywhere near zero. Okay. In terms of the aerosol effect, it's a huge error bar, and it actually comes quite near zero. Okay, so that could have a huge effect. If we're getting this wrong, that'll have a huge effect on how the forcing and the warming is being predicted by CO2. Are we actually cancelling it out? Are we not cancelling it out? So there's low scientific understanding from 2007. There was very few aerosol models. We didn't really know what was going on. All we knew is that it affects clouds. This error bar is huge. But then there was 8 years before the next Intergovernmental Panel of Climate Change report came out. A lot of global aerosol models have been built, lots more understanding. We know what's going on reasonably well in terms of how aerosols formed, the emissions that go up into the air, where they come from, and what happens to it while it's in the air. Okay? So in 2015, they produced another of these figures, but that aerosol uncertainty bar has not reduced at all in those 8 years, even though we know a lot more about aerosol. Okay? So why, if we know a lot more of it, are we not able to actually tell what's going on with the temperature still from aerosol? And it's actually now hitting zero. Okay, so it might not have any effect at all. according to the models. So we developed an approach which is based basically on the approach you've all been learning about here. We designed our science questions, and I'll go through each of these as I go along. So this is kind of like an outline slide. Expert elicitation, I asked the experts what they thought their uncertainties were in terms of those processes that are going on in the model. I sampled, ready to emulate, I emulated, and then I've done sensitivity analysis and constraint. So when I got to this point and did the sensitivity analysis, I became quite popular with the scientists. They understood their models much better. Now I've got to this point, I'm becoming less popular because well, you'll see why. Okay, so why did we decide to do sensitivity analysis? My boss at that time is an aerosol scientist, and he was really frustrated by those bars on the IPCC diagram. So I showed you two. I showed you 2007 and 2015. 2004, I think, was the same, and the one before that was the same, and the one before that was the same. So this error bar was not reducing at all, and it was kind of winding him up, I suppose. And also, he didn't know where that came from. Okay, different models say different things, but what is it that they're doing that's different to create that error bar? So he wanted an error bar that he could understand and that he could actually say, well, it's because of this and it's because of this. And he wrote a job application, and it was about sensitivity analysis. So I applied and got it, thankfully. But his question was, how can we produce an error bar for aerosol radiative forcing and target the research to reduce it? Because from multiple models, it's really difficult to target the research if you don't know where that uncertainty is coming from precisely. So what they were doing, as I've said, is just producing that error bar from multiple models. And then they were targeting their research on the most uncertain model processes or parameters, okay? But they didn't actually do the step that actually does that process or parameter affect what happens to the aerosol at the end, okay? We know we don't know much about this. Does it matter or not? That was where they didn't know anymore, okay? So the sensitivity analysis should tell us what matters, okay? So if something can be very, very uncertain, if it doesn't actually affect the aerosol that's affecting the clouds, then don't bother learning about it. So that was kind of where we were coming from. So the sensitivity analysis will help us to do that. And then more importantly, we could do it with our model. We can control the model runs in our model. It's deterministic. We give it a set of inputs, and we can get out the model. So we can design an experiment. You can't design a multiple model experiment in terms of those parameters. You can ask everybody to set them to the same thing, but because you don't actually know what's going on, it's not actually a designed experiment. And actually what actually happens is they give you their best model run and you don't know what those inputs were. And also these model parameters are statistically independent, okay? So without knowing the model output, we can put uncertainty on these parameters, and our uncertainty on one parameter will not be affected by knowing what another parameter is. Okay, and now later on that might change because we'll be constraining, but a priori they're independent, okay? So I'm not actually sure whether you went into sensitivity analysis or not. I'm sorry, I haven't been here all week. But we're just using these two indices here, the main effect and the total effect. So if our variance is made up of these different indices, the Wij, that's our sort of uncertainty from a single parameter, okay? Wi, sorry, and then Wij would be the uncertainty from two parameters actually together. So as long as we have statistically independent model parameters, our variance in Y can be split up into these sources. And the two that we'll be concentrating on are the main effect and the total effect. And altogether, these indices will add up to 1, right? And this is important as well, because this is how you can see whether there are interactions by only using these two measures. Okay, if all your main effects are adding up to 1, then there are no interactions. Okay, so the different parameters are not interacting with each other. The main effect, I'm not going to go into the technical detail of it, but essentially what we know is that the proportion of variance it would be reduced by if we learnt that parameter precisely. Okay, the total effect is measuring how much variance would remain if we learnt every other parameter precisely and not that one, and that then includes your interactions. So if your total effect is large compared to your main effect, that parameter is somewhere interacting with another one. Otherwise, it's just the main effect. Now, interactions get a bit confusing later on. So what I will tell you is that we found very little interactions in terms of the sensitivity analysis. It's main effects that count for almost everything. So we're really only looking at this main effect, how much the variance reduces by if you learn that one process precisely and its associated parameter. Okay, so how do we calculate these? Well, if everything works perfectly, you directly derive them, but these models don't work in that sort of way. There are really restrictive constraints on that, and these models just don't fit that. So we have to use sampling to get the enough samples to work out these indices, because we have to create that variance to be able to actually apportion it. So random sampling, we could do that, but it requires a lot of model runs. Even for a very simple model to create those indices, you'd need a huge sample. There has been work, thankfully, to actually break down the equations behind those indices and use an extended fast method, so we can actually calculate these with much fewer samples than we would if we do random sampling. Okay, but this is still too large from our global aerosol model. To do a single model run for 1 month, it takes 90 minutes. Okay, so my boss worked out how long it would take to do the extended fast method with that, and it was about 900 years. Okay, so we can't do it. It's simple. And then, of course, we've got this radiative forcing model to actually work out the temperature effect of it. Okay, so we turn to Gaussian process emulation. Again, I'm not going to go into the detail of that. I think you've heard a lot of the details on that. And if you want to know exactly what I did, you can ask at the end. Okay, but we've got these two model outputs that we're interested in, those cloud condensation nuclei. How many of them do I have in a single model grid box in any given month? Okay, and then from another model, I've got, okay, so what is the global mean radiative forcing from that, which is a proxy for the temperature change. Okay. Now, I've done it for every single model grid box in the cloud condensation nuclei, CCN, but I've only done it for the global mean forcing at this point. And then to do the elicitation, there are so many model parameters that we're uncertain about, we could actually just not be able to do it just by thinking about that. So what the experts did, or the aerosol modelers, was they thought very carefully about actually which ones of those might affect the CCN. So if it affects, so dust is not a good CCN, we know that. Dust is a direct effect, but it doesn't really affect the clouds. There are no clouds there, that process is already happening, and it hasn't changed much. Okay, so what model parameters do we expect? They managed to find 28 of them, and that made our problem sort of feasible, tractable. Okay, now one thing that they assume is that if it affects those CCN, it will affect that aerosol indirect radiative forcing. Okay, that's a given. If it affects the clouds, if the aerosol can affect the clouds, it must affect this radiative forcing. Okay, so if we learn about CCN, we'll learn about the radiative forcing. Okay, because the process is how one leads to the other. Yeah, if it affects the clouds, it's going to affect the radiative forcing. So learning about one must tell us about the other. Okay, so we built the emulators using every model grid box and a monthly mean CCN means I can use very simple emulators. I've broken down the problem so that I can just build thousands of emulators. 8,192 independent emulators tell me about the globe, okay? So all the pictures I'll show that are maps are independent emulators, and the spatial correlations between those actually carry through into the emulator. And the information is there, okay? I validate them, so I'll show you a little bit about how to validate them, or how I validated them. I'm not sure that there's a set way to do this. Different validation methods tell you about different things, so I did a few. And then you calculate your sensitivity indices. If you've got a valid emulator, you can sample from that rather than the model. So your 900 years turns into about a week. Okay, so there are different processes going on, the emissions, how many CCN are we sending up into the air, how are they interacting with the clouds, so aerosols sort of get more and more water on them, they grow, how does that affect the cloud? How are we actually modeling them, so you can't do, different size aerosol do different things in the air. How you split those sizes up and what they actually do, you categorize them, and then different aerosol do different things. How you categorize them, we looked at that as well. What happens to a drop when it actually becomes cloud? And then how is it removed? So we had these 28 parameters. We had lower and upper bounds on them, and they gave me a median as well, so I could put sort of a almost rough distribution on them. Because we're doing sensitivity analysis, we weren't too concerned about that distribution, as long as it was roughly the right shape and that the bounds were realistic. Then I use this Latin hypercube design, and the reason that I use this in particular, so this is a Sudoku puzzle, I've marked out all the fours, is that in a model like this, we had 28 parameters, but in any single model grid box, we don't expect all 28 to affect the aerosol. Okay, so there's going to be a lot of inactive dimensions in this. But because we're using this Latin hypercube design, those dimensions are still well sampled. Okay, so you can't really see it here, but these black points are our points, and then if you project those onto any of the marginals, you're getting a good sample. And then these red ones are a 2-dimension sample. So we're covering the space, basically. We're trying to get good model runs that we can interpolate between so that our estimates of the CCN or the radiative forcing are good. So I validated it. So this is a typical way of doing it. You take extra model runs, which I did, and then you see whether your emulated CCN matches the simulated CCN. Okay? And it wasn't bad. The error bars are reasonable on it. This is just one single model grid box. And I counted, because I have 8,192 models. Looking at that many pictures like that is tough. You get kind of bored after 3. So I counted how many of these points crossed the x equals y line. And then I plotted that as a percentage here. So over 90% globally crossed that line. So the actual emulator model is close to the simulator model. Yeah, that's right. And then to make sure that those error bars weren't so big that actually, yes, it would cross the line. Of course it would. They're huge lines. I did some simulations and made sure that those error bars were not very big. So generally, these error bars don't go further than 10% of the mean away from that line. So that's what I did there. These areas here, where you're not getting such good results, are actually because one single parameter is dominating and your emulator is a bit too confident in itself. Okay, but the relationship there is actually very well emulated, probably better than anywhere else. But there's one parameter dominating, and the emulator's a bit cocky. Okay, what's important here is we're not replacing the model. We often call emulators approximations of the model. They're not approximating the model, they're approximating that one output. They're approximating the monthly mean CCN in a grid box for a certain month, okay? So we can only predict that CCN for the certain month in that grid box. We can't take a grid box over the Arctic and say anything about the Southern Ocean, okay? And we can't predict what other models would predict. So this is all dependent on our aerosol model, which we think is a decent example of an aerosol model. Okay, and then we start to get results like this. So our emulated mean CCN in 2 different months. So these are from independent grid boxes. All the spatial correlation is there in the mean. And it looks like what the aerosol modelers would expect to see. Okay, so it's high aerosol over these regions where there's a lot of biomass burning over the Amazon. And that changes from winter to summer, so we've managed to capture that change. Not much aerosol over the Antarctic, we can see that, and it's hemispherically seasonally dependent. Okay, so we managed to get what we would expect from emulating rather than simulating. But what we get on top of it is the uncertainty bars from the uncertainty in those 28 parameters. Okay, so now I've called it emulator standard deviation. It should say emulated standard deviation. So it's the uncertainty in the CCN due to those 28 uncertain parameters and the sample that I gave it and the emulator that I built. It's high uncertainty over areas of high CCN is reasonable. It's what you'd expect. The numbers are going to be bigger. Low uncertainty over areas of low CCN. But what's important is what's leading to these, okay? Where are these pictures coming from in terms of those 28 parameters? So these are a few of the maps of the main effect sensitivity indices for different parameters. So this one here is how the aerosol is removed by something called dry deposition, so how it falls out. It's not rain related. So over these sort of equatorial oceans, this parameter is very important. If you want to reduce your uncertainty in CCN, you need to learn about this parameter. Okay, and that will reduce the uncertainty by over 50%. Okay, so you'll reduce your PDF of CCN for each of these grid boxes by over 50% if you learn that parameter in January. And then you get different parameters do different things. So this is one of the parameters that categorizes the aerosol and how that changes. That's kind of important everywhere, except for over these regions, which are the biomass burning emissions. So how much aerosol is released by burning of fires in the Amazon and South America and Africa, sorry, and also over Australia. And so the next thing we did was, actually those plots are on there, was try to cluster these. So like I said, not every parameter is going to be important everywhere, but sets of them are important in different regions. Okay, so we tried to cluster that just by simple k-means clustering of the main effect indices, and we found that all the main effect sensitivity indices are pretty similar across the Antarctic. Okay, they're all similar over these biomass burning emission regions, which changes between the months. So I've done this for the whole year. We've done 1 year model runs, and then they're all similar over anthropogenic regions where we're putting more carbon dioxide into the air, and with those in the power plants, we're releasing different aerosols. And then when we look at the average of those main effect indices over the different clusters, so we've named them, and then we've just taken every single grid box in that cluster, taken that main effect indice, and worked out the average of each of the 28 parameters. So there's 6 important colours there, really, that make up nearly 100%. So there's very little interaction in terms of the sensitivity indices. If we could learn this precisely, we'd reduce our uncertainty in CCN by approximately 20% over all southern hemisphere marine regions, okay? And what we found was that these main effect indices over all the oceans were pretty similar, okay? Over the Antarctic, they're very different to over the biomass burning regions, which is not surprising either. But we get this picture, and we can see where different model parameters are affecting the CCN, and we kind of get an idea of how our global model is behaving regionally across the world, okay? In terms of the forcing, so we've done that again, but only for the global mean forcing calculated by a different model. You see that actually the natural emissions are very important here, which we didn't see for CCN. So it was anthropogenic emissions were more important for CCN. Natural emissions are very important for forcing, okay? DMS flux is the ocean, so what phytoplankton release into the atmosphere. That's really important in terms of how our aerosol is affecting the climate, okay? Which is different to how we affect aerosol, okay? And that's because when I showed that plot with the background of white to grey, these are the two parameters that are affecting where we are on that curve, okay? These were important in the pre-industrial era, but they're not important now. And so that leads to a difference between the parameters that are affecting forcing and what's affecting the CCN. Okay, but like I said, the two concepts of CCN and radiative forcing and how they affect the clouds, they're directly linked. If we affect the aerosol, we affect the clouds, we should affect that forcing. Okay, so we want to constrain the aerosol because we can go out and measure it. And therefore we should constrain the forcing, okay? But bear in mind that I said the sensitivities are different, right? So we want to reduce the variance of Y by learning Y. We are not learning these parameters, we're taking aerosol measurements and we're trying to reduce this. But therefore we must be reducing the sensitive indices in here. So can we use these sensitivities to quantify how much we can learn from any CCN observation? Okay, if we can learn CCN anywhere, that will tell us about certain parameters. How does that constrain the parameters and how does that carry to the rest of the model? Okay. So the procedure that I've done is I've taken an aerosol measurement. And by aerosol measurement, I mean I ran the model under its median setting, called that a measurement, and then I've used that as a synthetic observation. And it's almost a history matching thing, but it's very, very idealized. So I just took that measurement, which isn't really a measurement, but it should definitely lie within the modeled region. So there's no structural error here at all. I added a little bit of uncertainty to it. I think it's 5%. It's a number I made up. And then I ruled out everything that did not sit near that region. Okay, so I start off with this CCN. This uncertainty is from the 28 parameters. Anything that doesn't lie in this region is ruled out. And I only have this CCN left. Okay, so rather than try and sample within this region how I got this region from the 28, I just take those 28, that original design, and only use the ones that give me CCN here for future. Okay, so I started off with 3 million, created this, and I end up with 140,000 parameter settings that give me CCN in this range. Okay, and then I measure how the standard deviation has changed. If I get a value close to 1, I've constrained my CCN completely in that grid box. If I get one close to 0, if it's close to 0, it's not constrained at all, so I haven't constrained the correct parameter sets. So if I take an observation in a grid box here, do that procedure, rule out everything that doesn't give me CCN within a very small error range here, run that leftover parameter set, so about 140,000 are left, and then run those through the emulators I built in every other single grid box, calculate the change in standard deviation. I see that I can constrain most of the world's oceans. Okay, if I do it in an anthropogenic grid box, I constrain the anthropogenic region. And that's not surprising because I'm constraining the same parameter set. Okay, so I've only taken forward parameters that give me the right CCN. Okay, and those parameters are pretty similar in any region of the world where we're dominating the anthropogenics. Now, if I run that through a forcing emulator, so I built these emulators with the forcing grid boxes. If I run that 140,000 sample through that, I don't constrain the forcing uncertainty anywhere, really. If I do it with the anthropogenic sample that I have left, then I constrain the forcing a little bit over the anthropogenic regions, but nowhere near as well as I constrain that CCN, even though they should be directly related. So what happens is my PDF here of CCN is much reduced, but when I run those through the forcing emulator, it's hardly reduced at all. Okay, so we decided, well, if we want to improve the way we're constraining forcing, we'll just use clusters that match most closely with the forcing sensitivities. So we know that natural emission parameters are controlling the forcing. So let's just find somewhere on the Earth where our CCN is dominated by those same parameters. And I should be able to reduce that forcing uncertainty. And if I use multiple clusters, somewhere in there I should get the right relationships that will tell me about the radiative forcing. So I did this. I hope this kind of shows up. But essentially, what you can see here is this is the one-to-one line. Okay, so if I'm constraining my forcing as well as my CCN, the dots will lie on this line. Okay. What you can see is that I can improve my CCN constraint without improving my radiative forcing constraint at all. There are some clusters where, if I learn about them, I learn about a bit more about my forcing, but nowhere do we get near that line. If I take 10 different grid boxes within those clusters, I still don't start to move up to that line. So I'm getting my constraint on CCN better, but I'm still not learning about this temperature change at all. If I take one grid box from every cluster, so I should be constraining a lot of relationships here, I still don't hit this line. These different sizes are me putting different amounts of uncertainty on that constraint. Okay, so in fact, I don't do half as well. And if I use different variables, all the ones that we think contribute to that radiative forcing, I still don't get higher than 50%. Okay, so what's happening? It's this thing called equifinality, right? So I constrain this. I've found a model grid box that's dominated by this particular parameter called Aitken mode width. My observational constraint tells me that that has to be somewhere between 0.5 and 0.8, okay? So I constrain my CCN very well. My CCN is about 600 in this grid box. In that same grid box, my forcing is dominated by my DMS, and this Aitken mode width does nothing to affect forcing. So that same parameter set just goes right across the width of my forcing. Okay, so although my CCN is very, very tight in here, if I take any particular part of that sample, I could get any forcing still. Okay. Another thing that happens is actually the sensitivities show that they're very similar. We have the same main effects showing up. The colours in those bar charts are pretty similar, but then I still don't get a constraint. I've constrained it to this relationship, so neither of these parameters are actually marginally constrained. But if I have a low value of this, I must have a high value of the other. And if I have a high value of this, I have a low value of the other. But that relationship is completely the opposite for radiative forcing. Okay? So if I go anywhere within here, I get CCN of about 700. If I put it in here, I can still get any value of my radiative forcing. Okay? So although theoretically we think they're directly linked, our model says they work completely differently. Okay? So this is where I got unpopular. Okay, so the constraint applies to the relationships, but it doesn't apply to the marginal uncertainties of those parameters. So if the relationships change, you still get anything across that width. If the sensitivities are different, then learning about one does not tell you about the other. So we have both of those problems. These aren't synthetic in terms of this surface has come from our model. These are real grid boxes. Okay, so this is really happening within the model. The parameter compensations are leading to the equifinality, and how we reduce that, I don't know. But learning the CCN from a top-down approach is not helping. Okay? And a model with constrained CCN is necessary, but it's not sufficient. You need a model that does CCN correctly, otherwise you wouldn't believe it at all. But that doesn't help reduce this aerosol indirect radiative forcing, and that's why that bar is not reducing. Okay, we're learning a lot more about the CCN, but that is not telling us about the forcing in the way that we thought it was. Okay, so there's wider implications on these, and I've really just mentioned them all. And this, I think, is a problem throughout all climate science models. Unless you have one particular parameter, maybe two, dominating, then this is going to be a problem. Okay? And what we really need is a new approach to this. Comparing the same comparing different models over and over again is not going to help. I think what we need is a bottom-up approach. We need to learn about these processes themselves. Okay, so one thing that happens a lot in climate science is calibration. We want to find one model and we want to know how that predicts in the future. But how can you possibly do that? We know that there's all those different model variants that are equally as good, and we know that the way that they predict the forcing is completely different. So that's going to affect how we learn about the temperature. So how can we do that? In particular, one thing that I've seen quite a lot in climate science is calibration. Then you take your posteriors, and if you've reduced your posterior range, then you say that that's a sensitive parameter. But like I showed, the marginals don't always show that sensitivity. Okay, so should that be used as a way of assessing sensitivity in a model? That it happens, but I don't think it's right at all, because all those relationships are hidden within the marginals. And how can a calibrated model be used for robust prediction, with or without uncertainty? And that's related to the question about how do you sample when you know you've got this space that's all funny shapes. So even if you try and include your uncertainty in those predictions, how do you sample from that funny, plausible space? Okay, so can we do anything about it? Well, yeah, I think we can. I think we can use the sensitivities to know which of those processes we need to learn about, which are the important ones. I think we should stop trying to use calibrated models for sensitivity analysis and for prediction. We really need model ensembles for prediction. We shouldn't be using calibrated models. So what I'm going to do in particular is try and do this same thing with multiple models and see whether the different parameter process compensations can give us more information on what's going on. Because I don't believe that we'll get the same result from every single model. Okay, but can we use the information from all of them to learn about this? Okay, And just a few further points on why I think this has happened. Well, our questions have changed. We built these models to learn about CCN and about aerosol. Now we're trying to use them to predict, and I think they're very different problems. So we're using them different. Our science questions have changed, and we're using the models in a way they weren't designed for. But our need to predict is becoming increasingly important, and these are the models we have. So we need to think about things differently. Unfortunately, well, yeah, model resolution is what climate scientists are aiming to improve. They think if we get finer and finer scale models, everything will come out in the wash. Okay, but equifinality is going to be a problem in all these models. So unless we start actually thinking about that as a problem in itself, then I don't think those error bars are going to reduce to what we hope they will. And we're still using old methods that we had when we were trying to understand rather than predict. We developed lots of methods, but now we're asking those methods to do new things, and that just doesn't work. We need new methods to deal with these new problems. And there's still not enough collaboration between us and them. I've had to learn a lot about aerosol modelling to understand what I've been doing, and they've had to learn a lot about statistics to know what I've been doing. And to do that, I sit down the corridor from them. And there's just not enough of that going on, and I think a lot of people are working under different assumptions here. And if you provide numbers to somebody, they'll use them how they want to use them, not necessarily in the way that you meant them to use them. So I think there's still a lot to be done, and that's it.
Time for a couple of questions. So quite get when you were looking at giving yourself a synthetic observation to constraint, how many observations were you giving yourself at once?
Okay. So to start with, these pictures just one. So I just ruled out everything that didn't match with that observation in that grid box. Any sample that was plausible, I ran it through every other grid box. Okay. In these that's what happened there. In these ones, I took 10 observations, and I kind of did it in a wave kind of thing. So it had to match all 10 within the error. And then these ones are 11, one for each cluster, and it had to lie within the error of all 11. So by this point, I'm getting very few points left over out of the 3 million, which is why I kept adding uncertainty. But actually, they seem to lie on a reasonably straight line. Yeah, and then that's 33. Got 3 different outputs in every cluster, and it had to match all 33.
What's that big red triangle one? Is that like your best result?
This is a different model output, sorry. So CCN are particles of a particular size, up to 50 nanometers, or over 50 nanometers. No, up to. And these are condensation nuclei, which are up to 3 nanometers. So they're much smaller particles, and only a proportion of those will grow to become the CCN. So we thought, actually, the CCN should tell us more about the clouds, but actually the smaller particles do. And that's because the sensitivities include much more of the natural emissions.
So something else I didn't quite understand. I might have misheard you. Did you say you shouldn't use calibrated models for prediction?
Yeah.
But you've got a model, and you've gone to your experts, and this is what they think about each parameter. And then, were you to get some physical observations, you would then be able to update those distributions a little bit, and it might not change them very much if information, but I mean, why would you not then use that model if you were going to use it before?
Okay, so so with the calibrated model, you're looking for one single model. So it's different to constrained model. Okay, so the constrained model here has all of these are within the constrained model.
Do you mean?
But calibration as in picking one of these to be the best.
Oh, right, oh yeah. Oh,
Yeah.
of course, yeah.
Yeah, there we go. But that's what they do.
Right, okay. Right, I see.
And they refer to that as the calibrated model.
They refer to that as the best model.
Ah.
So
Yeah.
in those error bars, they will have given the best model. So they'll have calibrated it in a different sense to what you were talking about. This is another problem with this collaboration is we all have different words for the same words for different things. And even within this, the word independent drives me crazy as well in interaction. It means different things at different stages of the process. Yep.
Just to check, sorry, thank you. So when you said you're going to use an ensemble of models, you mean to match these observations? We've actually got all these, if you like, we've got an ensemble of calibrated ones.
Yeah.
And you use them all to kind of make your...
Yeah, maybe not all of them, but you should at least have a sample out of this. Yeah.
Like the best of a...
Yes.
Not just one.
Yes, exactly. Yeah. And they are moving towards an ensemble, but the ensemble isn't being constructed like this. They're saying, right, we're uncertain of this parameter, so we'll change that top and bottom. That's 2 of our ensemble. So they're doing it differently to how I think it should be done.
Okay, go on. One last one. Go on.
Okay, thank you. If you look at these plots now, and they are unexpected in the sense that you said that one might have thought that CCN and forcing are like in the same direction.
Yes.
Does this now mean that the other parameters are wrong, or that the models are wrong, or that the underlying science is wrong?
I don't know about wrong, because I do think even in the real world, I think the equifinality will exist. Different, the same CCN could lead to a different radiative force under different conditions. I think we don't know enough about what those conditions are, and I don't think that unless we can model every single thing that's happening, we're always going to get something like this. I think basically it is a model resolution thing, but it's also an understanding thing, and I don't think we'll ever be at the point where we understand it well enough for this not to exist. So I wouldn't say wrong. I'd say that we'll never be in a position to understand well enough to be able to make this right, if that makes sense.
You may as well take another question while setting up. Yeah.
So this is very interesting. Thank you for the talk. I mean, we've been looking a lot in systems biology about designing future experiments to constrain parts of our input space in various ways. There's various ways to do this, and there's various ways to do it more rigorously and then do faster techniques. But I'm a little bit confused. I mean, is the problem that you're constraining yourself by realistic sets of measurements that one could do? I mean, if you were to just put in many, many measurements, would you start constraining these regions? I mean, if you were to theoretically measure every single output of your model at every time point, would it constrain those regions, or would it just not? The time period you're looking at is too short, doesn't it?
I don't think it will, because the CCN is different globally, and I think if you take lots and lots of CCN from one single cluster, the information content is not there. So it won't help us learn about the other clusters, okay? Except for the ones that match.
That can be measured then, which is not included in your model.
Yeah.
Which would constrain the thing that you really need to constrain.
If we could find it, yeah. But theoretically, there's no ideas on what that is yet. But even then, I mean, your model has to agree as well. Your model has to be doing enough for that relationship to exist.
Okay. Okay.
Right,
So
yeah.
let's thank Lindsay.
Yeah,
again.
I'm sorry, I have to go now, so I can't be in the discussion either. Sorry about that.
Okay.
Uh,
Thank you.